In today's session, would be taking one step further regarding the analysis of data that you can do with Microsoft Excel. In the previous two sessions, we have seen using pivot tables and pivot charts, and today we'd see how you can do linear regression using Microsoft Excel. Let us dive straight into it. As you can see in the first sheet, I have two columns. First is the year, and the second is the price of a house. And for each year, the average price of the house has been taken. So we want to, predict or forecast what would be the price of the house in 2004, let's say, or in 2005. So we would be using a linear regression model and later see if any other model can fit better if we use a polynomial model of order 2 or order 3 and see whether that would give a better prediction of price or not. So to start with, let us see how you can start with linear regression models. First, hold on a minute, I'm sorry. First, we will select this data set. Well, there are very few number of rows, but I think this will be a good, at least a good way to start and show you how linear regression is done. We select the data set and we go to insert and this chart, a scatter plot, and we'll be doing a scatter plot without connecting the dots, only the scattering of the points. We select this and we have this plot. Let me make it a bit big for you. Okay, so now we would want to change the scale so that we get a better picture. The x-axis seems to be okay. The y-axis we can start with 15,000, right, and end at 35,000. So I'll right click on this, format axis, and minimum I'll keep at 15,000, and this would go till 365,000. Okay. Great. So I can see the data points better now. So as you can see, this is not a linear curve, This curve is kind of constant here and then starts increasing from this point. Okay. So I would want to, fit a curve that would describe these data points, or that would try to, give an average value of how these points are moving across time. So what we can do is we'll go to design. So in this design section, you can actually make the chart look more, better for you, more personalized for you. So I can go to this where you see these changes to kind of diamond shapes. I can make it this one, this style, this, any style that's you find it better to visualize will be best for you. So I select this one, let's say, okay. And now the thing is, we'll go to add chart element, and we would go to trend line. In trend line, I'll go to more trend line option. And you see, the first thing that we'll be doing is display equation on chart and display the r squared value on chart. Okay, so the equation and r squared value is here. Okay, great. So this equation is basically, if you see, is of the form y is equal to mx plus c, where m is 188.1, which is the slope, and 2 minus 2e into 10 to the power 7 is basically the intercept. So that basically says that the slope is the rate of change of y-axis with respect to x-axis, which can be simply translated as per year the change in price of the home is $8188.1, and this is minus 2e to the power 10 to the power 7 is at zero value. Okay, so at year 0, what would be the value? So it goes to be a negative value, which is not possible, right? And so this data is starting from 1988. Okay, so we need not bother about this zero intercept. Okay, this is called the intercept, and this 8188.1 is called the slope. Great. Now the thing which we are more interested now is this r square value. This r square value here is 0.583, which is basically 58.3%. Okay, this r square value will tell you how much does the model, how much can the model explain the variability in this chart, or how well does this model capture the change in y-axis with respect to x-axis. How well does this model explain the variables in this chart? How well is this model capturing the change is basically defined by r square. It's basically the correlation that this model is having with the the actual data. So these circles are basically the actual data points, and this line is basically the model. So if I take a value like 1996, in 1996 this was the value of the home 174500, and if I move it to this point here, this point will basically tell me how much is the value, okay, this point of the model. Okay, so this r square is of our importance. So more the value of r square, basically I can tell the better is the model. So okay, so if this is the y value, what I can do is for 2004 I can do something like, this is the home price y, so y is equal to 8188.1 into the x value, okay, minus 2e plus 07. Okay, okay, so no, we can't do that, sorry. Okay, so now if I want to find out any other kind of model, whether it fits or not, I can double click on here and go to exponential, and it is now 60.4%. Remember, the more the value of r square, the better is the model. If I go to logarithmic, it's 58.21. Polynomial, since polynomial of order 2, so it's a x square function. Y is a function of x square, so it's now giving 95.54% as r square. So it's a great improvement from the linear model, right? The linear model was only 58% and polynomial goes to 95%. It's a great increase. So par is decreasing again. So polynomial order 2 seems to be a better one than the linear one. So if I increase the order, if I make it x cubed, it's 98.96%. X to the power 4, 98.96, x to the power 5, 99.42. So as I'm increasing the order, the R square value is increasing. But there is something called overfitting. We shouldn't be overfitting this plot. Okay, these data points should not be overfitted. So I can see order 2 is fitting it in this way. Order 3 seems to capture it much better, and order 4 doesn't. There is not much of a change between 3 and 4, right? And order 5, it kind of seems to, overfit the plot. These small changes, undulations seem to overfit. So 6 is like complete overfitting. So order 4 and order 3, which one? So it's always better to go with a simple model if you have the same R square or the value doesn't change much, because it saves computation time. So we'll go with order 3 in this case. Do comment if you feel order 4 or any other order makes more sense for you and why. So going by order 3, this comes out to be your equation. Y is equal to 121.35 x cubed minus 724,861 x squared plus 10 to the power 9 x minus 10 to the power 12. This is basically your equation for this line. Okay, and R square is 98.96%. So 98.96% of these changes in the graph can be explained or can be modeled by this line. Okay, so that was kind of a quick introduction. I can go to format and I can change the color to green, so it now looks much better to understand. So this is kind of a good plot which doesn't seem to overfit or underfit the points, and gives an R square of 0.9896, which is a good one for me. And okay, so let's do another one. Okay, kind of recap also. So you have city and the monthly riders. So how many riders or car riders are present in a city? We want to forecast that. So it's each month in a city, so Jan, Feb, March, April, May, each month, how many riders are there. Okay, so I can, what I'll do is I'll select this data set. I'll go to insert and I'll draw a chart. Okay, great. So again, I should scale this, to have a better look. The x-axis seems to be in a good scale. The y-axis, I can make it from 5,000 to 17,000. Let's do this. Right click, format axis. I can make it from 5,000 to, okay, it takes 17,000 automatically. So that's the beauty of Excel. It understands you. Okay, so this is my curve. So this kind of seems to be a linear one, but there are small changes. It's not a perfect linear model. So remember this thing, guys. In any kind of modeling or forecasting, we don't try to fit these points perfectly. If we fit it perfectly, then there are two cases. Either the data is not a practical data set, there's some it's a theoretical data set that you're using, or secondly you have overfitted your model, which is again a bad thing. So we never try to give a 100% accurate solution. What we try to do is basically give as good possible a solution, as good solution as possible. Okay, so going into this problem at hand, if I do the same thing, I go to design. You see one thing, quick layout. You can add these linear models and everything at your hand. It's very easy, but I'll prefer this one. Go to trend line, more trend line options, and let's start with exponential. So exponential. Okay, sorry. The first thing, display the equation and the R square value. Okay, so this is the equation and the R square value. Okay, so let's go back. Okay, exponential, this is equation 5885.3 e to the power 0.0414 to the power 14x, and this is the R square. So it's explaining around 96%, which is a good one, man. Linear is 98.9%. Awesome. And this is the equation. Great. Great. Logarithmic, oh see, logarithmic is 84%. It's a drastic decrease in R square value, and this curve doesn't seem to explain a little bit. Like, it doesn't even explain anything. So this is outright wrong. Polynomial of order 2, it's 99%. Wow, it's good, man. Linear was how much? 98.9. Polynomial is 99%. Let's change the order. Order 3, 9922. Order 4, 9944. Order 5 is 9948. So the R square value is not changing much. It can never be 100%. R square can never be 1 here, because it's not a theoretical data set. It's a practical data set. So there will be variations, you know. It's only that the model should minimize this variation, but keeping in mind that's not overfitting. 6 is 19952. So 6 kind of overfits it, you see. Let's start with 2. 2 seems to underfit it, you know. These changes, this increase, this decrease, these changes are not captured at all. 3, not much. 4, yeah. So 4, you can see, is kind of capturing this. It's going down, going up. So it's kind of capturing these changes, but again, not overfitting it. That's what I feel. You see. So order 4 seems to be a good choice here. Order 5, order 5 is also a good one. But 4, 5 and 6, not much of a difference, right? 6 I can feel is giving a bit of, you know, overfitting here. It's trying too hard. Okay, so 4 and 5, not much of a change. So let's stick with 4. As I told, simpler the model, the better. It decreases the computation time to a lot. So in this case, the data set is very small. But if you have a big data set, then you need a good computation time. So okay, so order 4 seems to be a better solution here. Damn, I should have done this change in color. Okay, so this model seems to be a better one. Do comment below whether you feel order 4 is kind of giving a better you know, model, is kind of modeling it better, these data points, or you feel that other order values can model it better. So if you like this video, do press the like button. If you want to see more of these kind of videos, do subscribe to my channel. Comment below what you find was interesting in this video, on what you feel should change in these kind of videos. We'll be meeting in the next video. Till then, peace.